For our ordinary differential equation example, we've got a microbe that's present in wastewater with an initial biomass concentration of X naught at time T naught equals 0. Experimental data shows the microbe's population is increasing at a constant rate K. Derive an expression for the microbe biomass concentration as a function of time, X of T. Okay, let's get started. Number 1, we've got to put these words into math. So our biomass concentration only depends on time. That's what makes this an ordinary differential equation, not a partial differential equation. So we have dx by dt, and it's increasing at a constant rate k. So that means the change in x with respect to time is going to be exactly equal to k, right? Our change is a constant. Okay, in order to derive an expression for the microbe biomass concentration as a function of time, we've got to solve this ordinary differential equation. So, step 2 of solving ordinary differential equations, getting all of one variable on one side and all of the other variable or other terms on the other side. So, let's rearrange this by multiplying both sides by dt. So I'm going to have dx is equal to k dt. All right, and we've done it. We've got all the x's on one side because we don't have any x's, and we've got all the t's on the other side because we don't have any t's other than our dx and dt. So now we can integrate both sides. So step 3, integrate both sides. So we're going to integrate dx, and we're going to integrate k dt. Now let's think about our integration bounds. We're integrating time from t naught equals 0 to some arbitrary time t. So we're going to have t equals 0 as our first bound and just t as our upper bound. For x, we're not necessarily going from x equals 0 to x equals x of t. We're going from our initial concentration, which is x naught. So we're integrating from x naught to x of t. That's how I'll write it. Okay. So integrating 1 dx just gives me x. And then I have to plug in my bounds. So I'll get x of t minus x naught equals k, or integral of k dt is just kt. So that'll be kt minus k times 0, since our first integration bound for t is 0. So obviously that's going to go away. And I'm just going to rearrange this over here. And to get an expression for x of t, I just have x of t equals kt plus x naught. And I'm done. Okay, so if we have a change in population with respect to time that's constant, just given by some constant variable k, that's going to lead to a linear change in our biomass concentration x, and our y-intercept is going to be our initial x concentration.